Bien, mesdames, messieurs, chers collègues, chers amis, cher professeur Bathe, nous sommes donc très heureux ce matin d'accueillir pour cette cérémonie de Docteur Honoris Causa le professeur Klaus-Jürgen Bathe, qui est professeur au MIT. Et je suis très heureux simultanément d'ouvrir la journée d'études et le colloque 40 ans de mécanique numérique à l'UTC. Notre université a décidé d'honorer le professeur Bathe, d'une part pour l'ensemble de ses travaux que je résume en mécanique numérique, mais pas seulement, aussi pour l'ensemble de sa contribution à cette discipline, mais aussi pour la vision humaniste qu'il porte. En lisant son curriculum vitae, je m'en suis rendu compte sur le rôle de l'université dans notre société, dans une conception d'ailleurs que je considère comme très proche de celle de l'UTC, notamment en termes d'ouverture sur et à la société. Cette cérémonie permet aussi, et je voudrais prendre l'opportunité, d'affirmer, et peut-être plutôt de réaffirmer haut et fort, quelques grands principes et quelques valeurs auxquelles notre université, mais aussi l'ensemble du groupe Université de Technologie, sont très attachés. Mais aussi, et j'y reviendrai par la suite, les valeurs de notre République. Tout d'abord, une ouverture internationale forte, notamment européenne, en tant que moteur de développement de l'interculturalité et de la pluriculturalité chez nos élèves ingénieurs, chez nos étudiants et sur notre personnel, et de creuser de ce qu'on appelle depuis quelque temps l'espace européen de l'enseignement supérieur et de la recherche. Et je ne peux m'empêcher à cette occasion, presque une semaine après le 13 novembre, peut m'empêcher, monsieur le professeur, mesdames, messieurs, chers collègues, de penser, dans le contexte de l'actualité donc de cette semaine, de cette dernière semaine, de penser que ce développement de l'interculturalité et de la pluriculturalité sur lesquels repose notre politique internationale est véritablement un rempart protecteur contre les excès idéologiques, en contribuant à former des ingénieurs, des docteurs, des masters, des scientifiques citoyens du monde, tolérants, ouverts aux autres cultures, au contact desquels on s'enrichit, chacun s'enrichit, et dont peut émerger une nouvelle humanité, une humanité humaniste. Je faisais référence aux valeurs de la République, il s'agit bien là de fraternité. Notre récipiendaire, au travers de sa nationalité, de son parcours et de sa mobilité intellectuelle et culturelle, que j'ai cru percevoir à la lecture de son CV, est tout à fait, de ce point de vue, en harmonie et en cohérence par rapport à ce premier attachement de l'UTC, cette ouverture internationale. Deuxièmement, un ancrage réaffirmé de notre université sur sa mission recherche technologique et innovation, au service de la formation, au service de la production des connaissances et de savoirs, au service du développement socio-économique et de l'attractivité de notre territoire. De ce point de vue, et je fais une seconde référence au contexte particulier que nous vivons aujourd'hui, cette crise profonde que nous vivons sur les plans économiques, écologiques, mais même plus profondément sur le plan moral, cette perte de sens finalement que nous vivons, qui ouvre la porte à tous les excès, à tous les extrémismes, au fanatisme et aux idéologies aveugles, nous incite à réfléchir aussi, tout ce contexte lourd, pesant, nous incite à réfléchir aussi sur notre propre rôle et nos missions en tant qu'université pour l'UTC, mais aussi en tant que grande école. Et sans bafouer les principes de ce qu'on appelle la liberté académique, l'on doit cependant veiller à ce que cette liberté académique s'exprime aussi dans un contexte de responsabilité par rapport à la société, de citoyenneté, de fraternité et de respect de la diversité. Deuxième valeur de la République, la liberté. Et pour terminer, sur ces valeurs, je poserai la question qui est la nôtre. Comment développer, comment concilier un développement universitaire qui n'oppose plus recherche fondamentale et recherche appliquée, selon cette dichotomie que je considère comme archaïque et dépassée et du passé, comme j'ai eu l'occasion de le dire au Césaire il y a quelques jours, qui n'oppose plus la production des connaissances et de savoirs et la création de valeur et d'activité, qui n'oppose plus recherche publique et recherche privée, qui n'oppose plus les acteurs universitaires et les acteurs économiques des milieux dont les finalités et les constantes de temps sont différentes. Bref, nous sommes là sur troisième valeur de la République, l'égalité. L'égalité entre tous ces concepts que je viens de citer. L'Université de technologie, professeur, est très fière d'accueillir en ce jour, dans notre cercle des docteurs honoris causa de notre université, le professeur Klaus-Jürgen Bathe, professeur à MIT. Fier parce que, selon les principes que je viens de rappeler, le professeur Bathe incarne parfaitement ces valeurs de l'UTC par sa contribution au monde de la science, mais pas seulement, des idées, de la culture et de l'éducation. Une telle contribution, que je caractérise de multidimensionnelle, représente en effet la marque et la signature de ce qu'on appelle le titre de Docteur Honoris Causa, pour rendre hommage à des personnalités étrangères éminentes. Une ouverture internationale forte, ai-je dit tout à l'heure, moteur du développement de l'interculturalité dans un monde globalisé. Une exceptionnelle créativité que l'on voit dans votre dossier, ainsi qu'en témoigne votre impressionnante production scientifique et les innovations associées. Une dimension humaniste d'un universitaire qui a été qualifié, dans l'honneur qui vous sera rendu, je l'ai vu, de professeur sans frontières et citoyen de monde. Et finalement, l'audace, qui est la cinquième valeur de l'UTC, de penser différemment, d'être impertinent, pour apporter des solutions innovantes à toutes les questions de notre monde, mais aussi du secteur de la mécanique, puisque nous ouvrons ce 40e anniversaire de la mécanique numérique, au travers de coopérations intenses et de synergies avec les milieux économiques et la société. Telles sont bien les valeurs que j'ai rappelées sur lesquelles se fonde et se construit le futur de l'UTC, avec la volonté de faire tomber les frontières géographiques, les frontières culturelles et aussi, je le réaffirme ici dans ce contexte, les frontières idéologiques qui musellent la liberté académique. Mesdames et messieurs, je vous demande d'applaudir et d'accueillir avec honneur et fierté le professeur Klaus-Jürgen Bathe. Merci. Et donc, vous avez reçu la suite du programme, donc je passe la parole au professeur Jean-Louis. On a toujours peur quand on entend des bruits en ce moment bizarres. Bon, tout va bien. Le professeur Klaus-Jürgen Bathe, donc, qui va prononcer l'éloge, comme on dit, du professeur Bathe. À toi, Jean-Louis.
Monsieur le Président de l'UTC, Monsieur le Directeur de l'école doctorale, Messieurs les directeurs du Laboratoire de Mécanique Roberval, Madame la Directrice de la Recherche ou Madame la Directrice de la Direction de la Recherche de Sorbonne Université, Monsieur le représentant du Conseil régional de Picardie, chers étudiants et collègues, Mesdames et Messieurs, c'est un très grand honneur de prononcer l'éloge du professeur Klaus-Jürgen Bathe du Massachusetts Institute of Technology, le MIT comme on dit, à l'occasion de la remise du titre de Docteur Honoris Causa par l'UTC. Je remercie la direction de l'UTC et toutes ses composantes, ainsi que ses instances, le conseil scientifique, l'école doctorale, le conseil d'administration, ainsi que les organisateurs du colloque 40 ans de mécanique numérique, qui me permettent d'exprimer mon admiration à une personnalité exceptionnelle du domaine de la mécanique numérique mondiale. Je connais Klaus-Jürgen depuis 1978. À l'époque, j'étais Research Associate au MIT et c'est le professeur Gilles Quentin, alors professeur visiteur à l'UTC, qui m'avait mis en relation avec Jürgen, car tous deux étaient des diplômés de l'Université de Californie à Berkeley. En 1978, Jürgen était au MIT depuis 3 ans et sa réputation de jeune enseignant-chercheur était déjà très établie. Il était dynamique, curieux, ouvert aux discussions et passionné par le développement des méthodes numériques pour la résolution de nombreux problèmes d'ingénieurs. Et après 40 ans, il a toujours cette passion. Il avait repris le cours du professeur Crandall, Engineering Analysis, qui avait été aussi la base de ma formation à Québec. Après discussion, je lui ai proposé un sujet de recherche sur la base de mes travaux de thèse avec Gouridat à l'Université Laval, et il en est sorti une belle publication commune. Cela a été déterminant pour ma carrière et ma notoriété. Une copie du rapport, Jürgen, if you remember. À cet instant, je souhaite en profiter pour rendre un hommage à la mémoire de Gilles Quentin, qui nous a quittés il y a une douzaine d'années et qui a si bien contribué au développement de la modélisation numérique à l'UTC en apportant chaque année et pendant près de 20 ans les dernières nouveautés des côtes Est et Ouest des États-Unis. Klaus-Jürgen est né à Berlin en 1943 et a quitté l'Allemagne à 20 ans après ses études secondaires pour vivre en Afrique du Sud différentes expériences de travail et d'études d'ingénieur dans un pays qui le marquera pour toujours. Il s'était auparavant déjà bien préparé au voyage en visitant la plupart des pays d'Europe, plusieurs pays du Moyen-Orient et du Maghreb. À 18 ans, il visitera Paris et la France à plusieurs reprises en se déplaçant en autostop. Vous avez, par les petits ronds rouges, tous les endroits que Jürgen a visités avant de quitter l'Europe pour aller en Afrique du Sud. Après une période de travaux agricoles dans les mines et sur les routes qui lui permettent de connaître le pays de l'apartheid, Klaus-Jürgen rejoint l'Université du Cap en 1964. Il y obtient un Bachelor of Science en génie civil en 1967 avec la mention Best Engineering Student and Gold Medalist. Il publie alors son premier article sur l'usage de l'ordinateur en calcul des structures. La trajectoire est dessinée. La prochaine étape sera le département de génie civil de l'Université de Calgary, au Canada, où il obtient en 1969 un master sur la modélisation, je dirais numérique, des plombiers. À Calgary, il fera la connaissance de Zorka, sa future épouse et son soutien constant dans ses activités professionnelles. Il fera également connaissance des professeurs Claff et Wilson, venus de Berkeley, pour un séminaire. C'étaient alors 2 pionniers de la méthode des éléments finis. Ce fut, je pense, une rencontre majeure, car Klaus-Jürgen décida de partir en septembre 1969 pour l'Université de Californie à Berkeley et y obtenir, avec une efficacité exceptionnelle, un PhD en 1972. Sa thèse concernera l'analyse dynamique des grandes structures en programmant la méthode d'itération par sous-espace, qui le rendra célèbre dans la communauté internationale. Ensuite, pendant 3 ans, comme ingénieur de recherche et consultant, il développe les logiciels SAP4 et NANSAP pour l'analyse non linéaire des structures par éléments finis. En 1975, le MIT lui propose un poste au département de génie mécanique. Il accepte ce poste et le challenge associé d'y développer une mécanique dite numérique. Il gravit tous les échelons des statuts de professeur et il est encore en activité comme professeur titulaire. Il aura été directeur de la division de mécanique et matériaux du département de génie mécanique, qui est un département très gros, fin des années 80 jusqu'en 1991. Maintenant, décrire en détail toutes les activités d'enseignement, de recherche, de développeurs de logiciels, de consultants, de conférenciers est mission impossible dans le cadre d'un éloge de quelques pages. Et pour notre invité, ce ne sera pas très passionnant. Il sait mieux que quiconque ce qu'il a déjà fait, et d'autres que moi lui ont déjà rappelé. Plusieurs bibliographies ont déjà été publiées, donnant tous les détails de ses travaux et contributions, comme le chapitre 7 du livre Giants of Engineering Science par Anwar Beg en 2003, et qu'il conviendra d'actualiser. Aussi, je m'attarderai sur les éléments qui sont à mes yeux les plus remarquables à signaler dans le cadre de cet éloge. Tout d'abord, Jürgen a toujours été stimulé et passionné par l'enseignement. Il a continuellement contribué au développement des méthodes numériques de problèmes de mécanique appliqués en structure, en solide, en fluide, en thermique, que ce soit en comportement linéaire ou non linéaire, en statique ou dynamique. Ces ouvrages, régulièrement actualisés, traduits en plusieurs langues, ont eu un impact considérable pour des générations d'étudiants de niveau ingénieur, master et doctorat à travers le monde. La liste est impressionnante. Numerical Methods in Finite Element Analysis avec le professeur Wilson, son directeur de thèse, en 1976. Finite Element Procedures in Engineering Analysis en 1982. Finite Element Procedure en 1996, puis en 2014, et c'est probablement le best-seller, je pense, de son ensemble de livres. Ensuite, il collaborera avec d'autres personnes pour également produire des ouvrages assez remarquables. Par exemple, The Finite Element Analysis of Shells Fundamentals, avec Dominique Chapelle de l'INRIA, ici présent. Inelastic Analysis of Solid and Structures, avec M. Kojic en 2005. The Mechanics of Solid and Structures, Hierarchical Modeling and the Finite Element Solution, avec Boukalem en 2011. Jürgen s'est impliqué aussi bien en formation initiale que continue, avec des dizaines de cours dispensés dans le monde entier, dont la France à plusieurs reprises, et notamment dans les années 70 et 80, et des collègues ont eu l'occasion de prendre ces cours dans les années 70. Les formats sont traditionnels ou modernes, ainsi qu'en témoigne la production de 34 cours vidéo sur le sujet Finite Element Procedures for Solid and Structures, with Study Guide, en 1982, avec la possibilité de les visualiser sur YouTube. Signalons qu'il a été primé à plusieurs reprises pour la qualité de son enseignement au MIT en 1986, 1999 et 2005. Alors, il y a bien sûr une cohérence et une complémentarité entre ses enseignements et ses travaux de recherche. Certains ouvrages récents sont largement inspirés des travaux de recherche. Les thématiques sont sensiblement les mêmes qu'en enseignement, en y ajoutant les interactions fluide-structure, l'électromagnétisme, la modélisation multiphysique et multi-échelle. Le bilan des activités de recherche est impressionnant, et les chiffres que je vais citer en témoignent. Plus de 300 articles dans les revues internationales avec comité de lecture, plus de 40 encadrements de PhD. Co-éditeur de la revue internationale Computers and Structures, qui publie un très grand nombre de volumes chaque année. Advisory Editor ou Associate Editor ou membre de Editorial Advisory Board de 17 revues internationales en mécanique numérique. Organisateur de 12 conférences biannuelles sur Non-Linear Finite Element Analysis and ADINA au MIT de 1977 à 1999, puis des conférences Computational Fluid and Solid Mechanics depuis 2001. Éditeur ou coéditeur de 4 ouvrages et des comptes rendus de 16 conférences. La notoriété scientifique du professeur Bathe peut se mesurer par les indicateurs internationaux, comme par exemple les 42 526 citations hier via Google Scholar. J'ai fait une capture d'écran de la dernière version. Et parmi elles, notre publication commune de 1980, citée 732 fois, et qui figure en seconde position dans la liste de toutes ces publications. Ce qui est entouré en rouge. Avant, ce sont ces livres. Et bien sûr, c'est une fierté réciproque. Faute de temps, je n'entrerai pas dans une description détaillée des sujets de mécanique numérique qui ont intéressé Klaus-Jürgen. Il y en a trop. En partant de la méthode d'itération par sous-espace que j'ai déjà signalée, pour aller, plus récemment, aux éléments finis de coque triangulaire MIT C3, de formulation récente donc, et utilisée actuellement par mes collègues du laboratoire de biomécanique et bioingénierie à l'UTC. Une autre activité majeure de notre invité concerne la valorisation de toutes ces activités d'enseignement, mais surtout de recherche. En effet, dès les années 70, Jürgen a été un développeur infatigable de codes de calcul et de simulation par la méthode des éléments finis. SAP4 et non-SAP à partir de 1972, puis ADINA dès 1974, alors qu'il était assistant research engineer à l'Université de Californie à Berkeley. Sans interruption depuis son intégration au MIT, Jürgen contribue au développement et améliore les fonctionnalités de la plateforme de modélisation ADINA. Celle-ci sert de base aux travaux de thèse, de master et de PhD de ses étudiants, mais également à des centaines d'autres à travers le monde. En 1986, Jürgen crée la société ADINA R&D, société d'une vingtaine de collaborateurs actuellement, avec une dizaine de représentations dans le monde. En Europe et en Allemagne en particulier, dans le cadre d'un partenariat privilégié avec Siemens, en Asie, en Amérique du Sud. ADINA est un logiciel présentant de nombreuses fonctionnalités originales et très concurrentielles pour de nombreux secteurs industriels traditionnels, ouvrages d'art, automobile, aéronautique et de haute technologie, en génie génétique ou biomédical par exemple, permettant l'innovation constante des produits, structures, systèmes et procédés. La philosophie du développement d'ADINA est fiabilité, généralité, efficacité. Ainsi, le professeur Bathe a su trouver le bon équilibre et la parfaite complémentarité des activités d'un enseignant-chercheur d'une université de technologie. Enseignement, recherche, valorisation économique et transfert. Mais une quatrième dimension des activités doit être ajoutée en ce qui concerne Jürgen. Il s'agit de celle qui consiste à contribuer au développement international du domaine de la mécanique numérique par des actions de collaboration et d'accueil de jeunes chercheurs, en majorité étrangers. Il a ainsi collaboré avec plus de 20 postdoctorants, dont je fus en 1978. Il a fourni les moyens financiers à une centaine de doctorants ou postdoctorants pour participer aux diverses conférences organisées depuis 20 ans au MIT, en particulier dans les 10 dernières années. Il continue de collaborer de façon étroite avec plus de 10 chercheurs confirmés, avec qui il a rédigé de nombreux articles et ouvrages, dont certains que j'ai cités précédemment. La dimension mécénat s'est concrétisée en 2014 par la création de la fondation Klaus-Jürgen Bathe Leadership Programme, permettant de soutenir financièrement une douzaine d'étudiants africains par an sur 4 ans pour poursuivre leurs études de bachelor, de master ou de doctorat dans tous les domaines proposés par l'Université du Cap, l'UCT, celle du début de sa formation universitaire. Le slogan de Klaus-Jürgen est « With good leadership, the dream of prosperity and peace for everyone will be realized ». Cette dimension humaniste me permet de qualifier Jürgen de professeur sans frontières, citoyen du monde. Une reconnaissance bien perçue par de nombreuses institutions étrangères qui lui ont soit délivré leur plus haut diplôme, soit attribué le titre de Docteur Honoris Causa. La Slovaquie, la Pologne, l'Espagne, la Roumanie, la Hongrie, l'Argentine et le dernier, l'Afrique du Sud, l'UCT et aujourd'hui l'UTC. Une question se pose maintenant. Comment a-t-il pu faire tout cela? Les réponses se trouvent en consultant ses proches, ses collaborateurs, ses collègues, ses étudiants, mais beaucoup d'entre elles peuvent être trouvées à la lecture du livre To Enrich Life, écrit par notre invité en 2007, et bien sûr qu'il va pouvoir encore actualiser, où il retrace sa vie, sa carrière et expose ses réflexions et leçons de sa vie. En fait, les mots-clés de son succès et de sa personnalité sont travail, je rajouterai encore travail, détermination, enthousiasme, attitude positive, sens des responsabilités, intégrité, fierté. J'ajouterai, pour l'avoir côtoyé, esprit sain dans un corps sain, car il n'a jamais sacrifié les activités physiques pour assumer de longues et intenses périodes de travail. Je suis très fier d'avoir rencontré Jürgen au début de ma carrière. J'espère que cet éloge vous a convaincu de l'immense talent du professeur Bathe, de l'importance de ses travaux pour la communauté internationale de la mécanique numérique, aussi bien académique qu'industrielle, de la richesse de sa personnalité, de son humanisme et de sa générosité. Il représente un modèle pour une université de technologie comme la nôtre, qui fait la promotion d'une éducation au service de l'innovation et de la recherche technologique, associant à la fois les sciences de l'ingénieur et les sciences humaines. Je souhaite, pour conclure, que la remise du titre de Docteur Honoris Causa au professeur Klaus-Jürgen Bathe permette une nouvelle dynamique de coopération entre le MIT et l'UTC, dans le domaine de la mécanique numérique bien sûr, mais aussi dans d'autres secteurs où l'UTC excelle. Je vous remercie. Je voudrais rajouter un petit point en préalable, c'est que Jürgen nous a encouragés à nous exprimer en français. C'était plus facile pour nous, je pense, et j'espère que ça vous a aussi permis de comprendre tous les détails. Merci.
Bien, merci Jean-Louis. Nous invitons maintenant le professeur Klaus-Jürgen Bathe à répondre à l'éloge qui vient d'être prononcé par le professeur Bathe.
Merci beaucoup, Jean-Louis, pour un très grand effort. Et aussi merci beaucoup à vous, Monsieur le Président. J'ai compris tous, mais je ne parle pas très bien le français. Je voudrais bien vous remercier pour la plus merveilleuse occasion. Pour recevoir un doctorat honorifique de cette grande université. Je considère ce doctorat un très grand prix. Merci pour les discours et pour tous les efforts. Il est formidable de voir tant d'amis ici. Comme beaucoup d'entre vous le savent, j'aime la France. Et j'ai été en France à de nombreuses reprises. Je suis très heureux de recevoir cet honneur maintenant ici en France. Et je suis très heureux d'avoir dans quelques minutes une occasion de vous adresser un discours. Alors que j'ai essayé de garder mon français et améliorer ma connaissance de la langue, ce n'était pas facile. Et donc, pour ma présentation, et maintenant, je vais me tourner vers l'anglais. Tous mes diapositives sont également préparés dans cette langue. So let me turn now to English, which is much easier for me. I'd like to express once more my great thanks to Jean-Louis, who has done a superb summary of what I've been doing. Of course, as he also very nicely pointed out, very well pointed out, I was only able to do so because I had fantastic collaborators, including him. Fantastic students, fantastic collaborators to work with. Dominique Chapelle is here. And it's all of that that has really made it possible for me to accomplish what you have heard about. It has been a great journey, and it is, as I just said in French, really a great honor to obtain the doctorate here in France. France has always been very close to my heart. My friends know that, and therefore I am very, very happy to be now here and be honored in France. Thank you once again, Monsieur le Président, and thank you once again.
Monsieur le professeur, vu la délibération du conseil d'administration de l'Université de technologie de Compiègne en formation restreinte en date du 21 mai dernier 2015, vu l'avis positif émis à la suite par le ministère des Affaires étrangères en date du 5 juin de la même année 2015, je suis très heureux de vous décerner le titre de Docteur Honoris Causa de l'Université de technologie de Compiègne et de vous en remettre le diplôme, en vous remerciant de la formidable contribution qui a été exprimée tout à l'heure à la science, mais aussi plus globalement au lien avec la société et les différents milieux, et notamment les milieux économiques. Merci beaucoup. Nous allons vous remettre aussi un cadeau pour vous remercier au nom de l'UTC. C'est un premier cadeau. Un second cadeau va venir et ensuite, avant la présentation de votre conférence dont on vous remercie, nous aurons un intermède musical par des musiciens qui sont personnels de notre université. Voilà. Alors, il y en a beaucoup. Je vais simplement, symboliquement, vous en remettre un ou deux. Voilà, vous pourrez prendre connaissance. Ça a l'air d'être un livre, vous voyez. Je vous le laisse. Voilà également quelque chose qui ne ressemble pas à un livre. Nous vous invitons également à en prendre connaissance. Et il y a également d'autres cadeaux qui continuent dans ce petit sac que nous vous remettrons. Je vais vous dégager. Voilà.
Merci beaucoup. Merci. Merci.
Bien, l'intermède musical. nouveau pour ces merveilleux musiciens que j'avais déjà entendus samedi soir à l'occasion de la remise du prix Roberval au Théâtre Impérial. Bien, je vais inviter l'honorable assemblée sur cette tribune à rejoindre peut-être le premier rang pour éviter, puisqu'on est dans le domaine de la mécanique, la mécanique de rupture du cou lors de phénomènes de torsion. Nous proposons un second intermède musical qui précédera donc la conférence du professeur Bathe. merci pour ces merveilleux moments. J'ai vu que le professeur Bathe a beaucoup apprécié, il chantonnait, je l'ai vu, donc merci beaucoup. Et donc, sans plus attendre, je lui passe la parole pour sa conférence dont le titre apparaît ici, donc Frontiers, open also,
yeah.
in Finite Element Procedures and Applications. So you have the talk.
Yeah,
Thank you very much.
Thank you very much. What a wonderful music. Maybe we should have become musicians. But I like to now address you with this title, Frontiers in Finite Element Procedures and Applications. And what I would like to do is share with you some of the experiences that we have been gathering during the recent years. The content of the presentation is summarized here. Briefly, I'd like to talk once more about the philosophy that we adopt in our research and developments. Actually, Jean-Louis already summarized it so nicely. Then I'd like to talk about our advances in the analysis of structures and multiphysics problems. And I'd like to emphasize really many outstanding research challenges. Sometimes the field is being represented as, well, much has been done, there is very little to be done anymore. But actually there is still a lot of work to be done. And then I'd like to conclude, and I'd like to also note that the results shown here are due to many collaborators, due to many works that I have been accomplishing with others, and there are too many names to list really. If you are interested in seeing more details and also seeing the names of these brilliant students and colleagues I've been working with, please go to my MIT website. Our research and development philosophy is summarized once more here: to develop reliable and efficient procedures that can be used in general, and to advance simulations as practiced in industry and the sciences. And here I'd like to emphasize that in industry, a designer needs reliable results. She or he must have reliable results because physical testing is frequently just not an option. Think of a huge bridge like the Golden Gate Bridge. You can't physically test such a bridge, of course. And so we need reliable results than when we run finite element codes. We should never forget that really what we're doing is to model a physical problem that we model given by a mathematical model which is governed then by differential equations, and then we obtain the finite element solution and we interpret the results. This is, of course, a very elementary slide that I show when I teach finite elements in one of my first lectures. But it is so important to keep that always in mind. As engineers later on, we might forget about the fact that we are really operating with finite element methods on a mathematical model trying to predict the physical problem. Our focus has been on the analysis of solids and shells, general structures, and when I say general, really from the kilometer scale to the nanoscale. I will talk a bit later on about the analysis of nanoscale structures. And of course, we're looking at multiphysics media governed by Navier-Stokes equations, Maxwell's equations, and of course the structural equations. And we look at the fully coupled response. The analysis of shells is still of great interest to me. Some of us, like Dominique Chapelle, myself, and Jean-Louis Bathe, we are all still locked onto shells. There are so many fascinating still problems to be tackled and solved. I talk about that a little bit. I also like to talk a little bit about the use of incompatible modes, which are widely employed in engineering analysis, and sometimes with methods that are widely employed in engineering analysis, there are still some surprises. I like to talk about the development of overlapping finite elements. I think this development is very exciting, and I can see that as a new paradigm for finite element analysis. I will talk about that. The solution of multi-physics problems, and then the modeling of proteins and DNA structures, in other words, going to the nanoscale analyses. The need for reliable finite element analysis is exemplified here. When we want to protect our brains with a helmet, for sure we clearly need helmets that work well, that have been reliably designed and analyzed. And so we spend a lot of time in the laboratory testing, in the simulation of these helmets to make sure they are really excellent helmets. And then we go into practice and we see that the youngsters do this sort of thing and don't wear helmets. And they don't wear helmets. And so one asks oneself, well, there is still something more to be looked at. And then we see here a bicycle race north of Italy. And these guys, they do actually wear helmets. But as you can see, somebody got upset there. And that person really needs more than a helmet, needs a swim vest as well. A swim vest as well. So, but anyways, it's always good to look at things a little bit from the humoristic side. And let's go now though on to the other point. The analysis of shells. Testing of elements is extremely important. When we consider a solution scheme, we want convergence to be optimal for all problems and independent of the shell thickness. And that really means for shells that are membrane dominated, that are bending dominated, that are intermediate, we want always that we have a very good or small error rather, which is proportional to a constant C independent of the shell thickness, H being of course in that formula given here the size of the element, and K the polynomial order of interpolation. And there already is a difficulty in measuring just the error. We use in general a mixed formulation, and for a mixed formulation like given here, I don't think I need to go through the details. Surely you are familiar with this sort of statement in structural analysis, very widely used now with the bilinear forms A, B, C, and the linear form F. We are looking in finite element spaces for a solution, and we know we need to use the mixed formulation in order to be able to tackle problems from bending dominated to membrane dominated problems. We must have no spurious modes, we must have consistency, and we want optimal convergence, which means that ideally the in-soup condition is satisfied, the relevant in-soup condition is satisfied, but here we are still struggling for general meshes and general geometries to satisfy the in-soup condition. Particularly, we also want a scheme, a discretization scheme, that does not use any artificial numerical stabilization factors. Because in engineering practice, as I said, we want reliable results, and we don't want these results to be dependent on artificial factors. The question of what norm to use in the measuring of the error. Point values are meaningless. Differences in energies are also not good when we are looking at a mixed formulation, when we are trying to understand a mixed formulation. The error can be positive or negative. The S norm that is defined here is valuable, in which we have been using for all types of shell problems. It can be used for membrane-dominated problems and also bending-dominated problems. Basically, we are just integrating the stress error times the strain error over the domain of the shell. So that is a very nice error measure. And then it is very important to test whatever elements we have on good problems, as we have published, particularly Dominique Chappelle, of course, has been really pushing forward on this field, and I have been sort of trying to keep going along with him in this area, but it has been wonderful to work with him here. The hyperbolic shell test problem is the one that we have been using abundantly for the testing. You can see it's a doubly curved shell, and we're using fixed boundary condition and free boundary conditions to have a membrane-dominated problem and a bending-dominated problem. And so then we have boundary layers to also mesh, as indicated here. And we use this sort of mesh for our three-node element, a three-node triangular shell element. And we mesh only 1/8 of the structure because there are symmetry conditions for the loading that we're using. It's a smooth loading around the circumference. And so we can use symmetry conditions for the analysis of the shell. The details are given in our papers. And here we have now developed some time ago what we called an MITC3 element, meaning the mixed interpolation of tensorial components is used, the method that we have been working with. And the element has 3 nodes. But then we found that that element works very well for regular meshes, but when we distort the meshes, it doesn't work well anymore. So we had to develop an MITC3 plus element, basically improving the 3-node element. And this MITC3 plus element is much better, as shown here. On the left, we have a fixed structure. On the right, we have a free structure. And we have pretty much good convergence. Of course, notice that we're measuring here the convergence as the thickness of the shell T is decreased. T over L gets, in other words, smaller. And that is very important. You want to see, ideally, you want to see, of course, no change in the convergence rate for T over L becoming smaller and smaller. And here we can see that left fixed structure, right free structure looks good. Our 4-node element, the MITC4 element, is also performing very well on this problem with regular meshes, but it's not good enough for highly distorted meshes, and so we have been working here too on an MITC4 plus element, in other words, improving the 4-node element. That MITC4 element is used very widely in many finite element codes, but it doesn't work well when the meshes are distorted. So when the non-distorted mesh is used that I showed you just now, we get good results with the MITC4 plus as well. And when we now distort the meshes, as shown here, highly distorted meshes, we ideally would like to also have excellent convergence. And you can see for the MITC3 plus, not bad, not bad. Of course, not ideal. The ideal curve is given by the solid line, but the MITC plus for the fixed and free structure works quite well here under these distorted meshes. The MITC4 element works quite well for the fixed structure, but the free structure being, in other words, bending dominated, for very small thicknesses, as you can see here, it still doesn't work well enough. So we are still working to improve this element. We still have ideas of how to actually get better results than what we have here. So you can see even for the basic shell elements, there are still improvements necessary. General shell elements that of the kind that I just talked about, of course, do not include the thickness deformations in linear and nonlinear analysis. And in some analyses, we, however, must include the thickness strain and stresses, like in metal forming analysis, in contact problems. And then the 3D shell that I can show you here now is actually quite effective. You see here the shell mid-surface, top surface, bottom surface. We have control vectors to control the deformations at the top and bottom surfaces. And here we have a simple analysis that shows really the power of the elements that we have developed. The MITC4 extended, in other words, to the 3D shell analysis. You can see here how the mid-surface moves. That's very important to take into account. In other words, to have the movement of the mid-surface is very important. And these results are really excellent. If you think you have a 3D shell element, try to solve this problem. This is the crushing and crashing of a tube. We are using implicit time integration. Implicit time integration is really much more reliable than explicit time integration. We all know about the explicit time integration having the stability problems. And here we use the elements, the 3D shell element, to analyze this type of problem. And here you can see a movie where the structure folds really down in implicit time integration once again with all these contacts involved. Not an easy thing to do. The mean force quasi-static analysis here compares very well with the experimental results, as you can see here. Even the peak is quite well predicted, the peak given right there. This is the analysis of a door crush problem. Again, we use the 3D shell. These are the different parts, how to model the problem. And here you see a movie where the parts are taken apart, but the deformations in each of the parts are shown, as you can see here. And here you see also the methods that we use: self-contact, double-sided contact, automatic time stepping, of course, and the 3D shell element. And the interesting part really is that if you try to analyze that without use of a 3D assumption, in other words, you just use the shell and element without the through the thickness deformations to analyze the collapse problem here, the door crush problem, I should say, you can see that by simply trying to update this through the thickness strain for the large deformations, you cannot get really the peak that you are interested in. The peak you can only be predicted if you use a 3D shell. Without that, including the strain through the thickness explicitly in the stiffness matrix and the force vector and so on, you cannot really get the peak deformations. So that is a nice example to show that. I'd like to talk a little bit about the incompatible mode elements that I'm sure you're all very well aware of. I like to point out that with these elements, there's really some special care to be taken, which engineers frequently do not know of. Here we have simply the analysis of a power screw on a nut. The screw, of course, shown in the middle, the nut on the sides there. And here's a mesh that we use to represent the nut, or the screw rather. And the screw on the nut itself is given by the rigid target surface. Here you can see a cut through the structure. The effective stress is given here before suddenly a spurious mode is triggered. This was a surprise to us, a great surprise to us, because this element is widely used and one would think it's reliable, but suddenly a spurious mode comes up. In fact, we were given this analysis by one of the Adina users, and we had to really dig and think what's happening here. And what is happening is that after the spurious mode is triggered, you get these type of results, just a step along. And so we analyze this problem then with the 8-node incompatible mode element, ICM incompatible mode element, the ordinary 8-node element, and also the 8/1 element. The 8/1 element is actually 8 nodes for displacements and 1 internal node for the pressure. And you can see here that the reaction force versus vertical displacement is followed quite nicely initially, and but then there is suddenly here, of course, the 8-node element here, the ordinary 8-node element is stiffer, too stiff as we would expect. The 8-node element in compatible mode goes nicely along here with the 8-1 element, and suddenly there's a bifurcation here. And that's where this spurious mode is triggered. So we analyzed that situation and we came to a very simple conclusion, which on hindsight one says, well, it's obvious. But what we did is we just looked at a 2D case. L2, as you can see, one dimension, L1 is the other dimension, unit thickness, planar element. If we impose a homogeneous deformation first onto that element, you can see here the homogeneous deformation to this direction and that direction, vertical and horizontal. Then the incompatible mode can, of course, be triggered like shown here. There's nothing for this element not to undergo this mode. And when we analyze the situation, we find actually that there's a key formula, that the strain in the longitudinal direction and transverse direction, epsilon 1,1 and epsilon 2,2, has a critical value at which bifurcation occurs. And that bifurcation occurs when L2 over L1 squared is reached. So the longer the element, L1 is the length of the element, the longer the element, the smaller the strain at which this bifurcation is actually going to kick in. And the interesting part is it's not just epsilon 1,1 that matters, it's also epsilon 2,2 that matters as well. That's, I think, also a very interesting point. So when we look at that formula and we look at the mesh here, you can see there are very long elements here, and these elements suddenly buckle out. And so all I wanted to show you is this experience that one has to actually, in this particular case, with these elements, widely used, widely accepted, still to be quite careful. We earlier looked at some implicit time integration analysis of this crushing of the tube. I just like to point out that we're using a time integration scheme that we find very effective lately, where we actually take for a whole step 2 sub-steps. And this means some more work per step, but the method is actually much more accurate than, for example, the Newmark trapezoidal rule, very widely used, and other techniques. So we take the trapezoidal rule for half the step, and then we'd use an Euler backward method for the other half step. And this method turns out to be very efficient. I will show you just now some results. First of all, we realize that there are no parameters to adjust. Simply the time step has to be sufficiently small for accuracy. The method solves in nonlinear analysis when other methods like the trapezoidal rule fail. And excellent accuracy characteristics are seen with this method. It's effective in the analysis of problems, in structural dynamics, and also in wave propagation analysis using implicit time integration. Here, a very simple problem. I always like to exemplify things with very simple problems. There's a stiff spring on the one side here, K1, very stiff spring, and on the other side we have a very flexible spring, K2. This is really representing a large finite element model with, say, millions of equations, where you have some very stiff parts and some very flexible parts. The stiff parts could be artificial by having introduced certain beams to a couple degrees of freedom. Stiff beams, it's being done in practice all the time. And so the K1 equal 10 to the 7 would represent such very stiff parts. We impose R1 and we want to solve the response. And if you look at the accelerations, you have some great surprises. With the Newmark method, you can see wild oscillations, these red wild oscillations. Of course, you can put damping into the structure, but then you have to ask yourself how much damping to put in. Or you can use different Newmark parameters. Again, what parameters to use. But the point is here that with the new method that we designed, we get very good results directly. Here you see the blue line is the result that we're looking for, and the others are all oscillating. There's an over or undershoot here in the first step with the new method, but that undershoot can also be taken away by setting the parameters in the first half step simply to 3/4 and 1 in the Newmark method for that half step. This method turns out to be working very well. We have made that, for example, now in ADINA the default. I like to talk a bit about solution of wave propagation problems. And here, of course, we have to have effective time integration and effective spatial interpolations. An interesting approach that we have followed is to enrich the spatial interpolations of traditional finite elements or overlapping finite elements, the ones I just mentioned earlier, by harmonic functions. That works very nicely. Issues in the discretizations are, of course, what mesh to use, what CFL number to use with the time integration scheme. And we know that traditional finite elements are quite sensitive to the CFL number employed in wave propagation problems. The overlapping finite elements that I'm going to talk about now show a lot of promise there as well. What do I mean by overlapping finite elements? Here actually it is simply the method of finite spheres that you might know already, but we have now generalized that we can also have not just spheres, we can take quadrilateral elements, trapezoidal elements, they can overlap. And that is, I think, a very effective way of approaching different type of problems. The interpolation functions are given here, where you have the shepherd functions, of course, and then the additional functions that you are associating with the interpolation functions. Here you have additional functions, polynomials typically, and that gives you then the total interpolation. We can also include harmonic functions, as I mentioned, for wave propagation problems. We have done that, and that turns out to be quite efficient for wave propagation problems. Here we have some results of simply a source applied here, 1/4 of the structure being analyzed, the wave propagates out, and when p is equal to 1, that means we only use the lowest order of interpolation in the polynomials. P equal to 2, 1 more included, 3, third term included, and you can see that for different types of meshes we get here good results. Of course, one has to ask which mesh to use and what interpolation to use, but here all of these particular cases work very well with the analytical solution, or compare very well with the analytical solution. The important point here is these observations. There is no need for use of an optimal CFL number. We simply need to use a small enough time step. That is, I think, very important, because in engineering analysis of using traditional elements, 4-node elements in 2D, 8-node elements in 3D, you have to use a good CFL number. Of course, the CFL number is given by delta T over delta T critical, and the delta T critical is given by the wave speed. Now, remember that for problems of wave propagations, you have S waves, you have P waves, you have Rayleigh waves, and then there's always a question which wave speed to use in the CFL number. And you can't get away from that. Whereas if you don't have a restriction on the CFL number, it is a much more effective approach to solve wave propagation problems. Let's look at the computational efficiency. In this particular problem, actually, it turns out that the procedure that I just showed you is very efficient. If we look at, for example, an error that we would like to have of less than 4%, then we can see here that for this error, we need a solution time of roughly 50 seconds with the method of finite spheres. If we use traditional elements, we also need, for that sort of error, also around 50, 60 seconds. So it is quite efficient here. The reason is, of course, that we are setting up, in this linear analysis problem of a wave propagation, we're setting up the stiffness matrix once. That's where a lot of computations are lying. And then we're going time-stepping through the response, which then is there's no more numerical integration required. And that's why, in this particular analysis, the method of finite spheres compares actually quite well with the traditional finite element method. Here you can see also that for the method of finite spheres, if the time step gets smaller, as you can see here for p equal to 3, a 9 by 9 mesh, as the time step gets smaller from here to there, the error reduces. And that should really happen. Every engineer would expect that without going into the details of the CFL numbers. Now here, for example, with the CFL number 1, you can see you have this error, and with the CFL number 0.5, you have a larger error. So a smaller time step gives you a larger error, and that is, of course, not something that engineers like. So I really believe that these method of finite spheres, these overlapping finite elements, are very useful for this type of analysis. Let me go on to multiphysics simulations. Fluid structure interactions, electromagnetic effects we have been focusing on. There are many, many types of problems that, of course, are falling into fluid structure interaction and into the electromagnetic analyses. The structure has one mesh, the fluid has another mesh, totally different meshes. That's very important, that the fluid nodes here, the small dots, show the mesh of the fluid. The structure here are the big dots. So we have a mesh, totally different mesh on the fluid side than on the structural side. We are solving the general Maxwell's equations, Faraday's law, the Ampere-Maxwell law given here, Gauss laws. These equations look harmless. They look simple, one would say, where E is the electrostatic field, H magnetic field, J, of course, the current, and so on. But when you really go into the details, you find out very difficult to solve, very difficult to solve. There's, of course, a Lorentz force per unit volume in the fluid or in the structure. There's Joule heating given. That also has to be taken into account when you want to analyze structures with electromagnetic effects. And it's an extremely rich field for a lot more research to be done. How do we obtain governing equations? There are many different approaches. We are actually using an approach where we have E and H, the electric and magnetic fields, as variables. The sources are K and J in these two cases. And in general, of course, we have strong coupling. We're converting the first order equations to second order equations that we can then actually convert to a form which is given by the divergence equations given here, which is then drawing, and then which means that we can then draw nicely on the knowledge that we have obtained in the solution of Navier-Stokes equations. We have also the additional parameters P and Q that we are introducing here. And so this set of equations now we are tackling with the same approach that we're using to solve Navier-Stokes equations, where of course we also have a divergence operator, and then we have also the pressure there as a physical variable, however. We can then solve problems like ablation. Here's a lab setup where the patient is, as you can see, lying down, and there is here an ablation where the lesion is to be taken out with a catheter, and here we have typically, these are the modeling parameters. Basically, of course, by Joule heating, we are taking out the lesion. Then here you have, with increasing flow and increasing power, the different temperature fields being generated, and that's what people are very interested in. The design of these catheters, for example, they need to know this sort of need to have this sort of information. This is electromagnetic heating of milk. There's a flow inlet down here, there's a flow outlet up there, there's a waveguide here, electromagnetic waves are going through it, and they heat the milk as you push it through. Here you can see the electromagnetic waves. Very interesting coupled problem, and then you can draw relationships, temperature versus the average temperature as a function of velocity. And here you have the distance, temperature is vertical, distance horizontal, and you can see that, of course, as the velocity is slower of the milk, you get more temperature increase. With higher velocity, you get the least amount of temperature increase. So because, of course, the milk stays longer in the channel at a lower velocity and will then be heated more. Let me turn over to the finite element simulation at the nanoscale, a very interesting field. Here we are analyzing with finite element methods proteins and DNA structures. This is work in conjunction with my son, who is also a professor at MIT. The finite element methods can here be very effective in the analysis of these structures. There are many basic applications in biological engineering, in energy engineering, in medical sciences, and it's really a huge field for a lot more work to be done. Here is an overview from the US Department of Energy, where you can see how basically the DNA structure here is given, and these DNA structures, they actually combine to give us proteins, and then the proteins, of course, combine for actual cells. And ideally, we would like to analyze the DNA structure, proteins, cells, all, of course, together, but that is a huge undertaking, as I want to point out. The analysis of proteins gives us understanding because it explains mechanisms of disease, and it's also very helpful in the development of therapeutics. And the analysis of DNA structures is really very important for the understanding of nanostructures in medical sciences and in energy harvesting. The most basic approach is, of course, to simply use molecular dynamics. Molecular dynamics is a very general approach, but it's extremely expensive. You can only really perform it on very small, non-complex nanostructures. The way to go is to use Langevin or Brownian dynamics. And with this approach, combined with the finite element method, we can really solve then, of course, small DNA structures, but also supramolecular assemblies. Here we have a structure, a protein structure, up here on the left, and then we have a surface representation given here. The molecular this surface representation comes from the molecular surface. We mesh then the inside, and let me just show you. We mesh then the inside, and we can then analyze. This is here the actual kinase. In other words, this is one of the proteins in open and closed conformation. The protein is open first, and then it closes. And what one would like to know is, understand is the mechanics and dynamics of that closing action. Here you have a movie of the results. You can see how the protein actually here closes. In other words, it was open first and now it closes. The equations of motion that are solved are given here. The M matrix, the mass matrix, K is the stiffness matrix, Z is the damping matrix. And the Z is very important because proteins, of course, are in water, they're in fluid, and that's where the damping comes from. The material properties for the stiffness matrix are obtained from molecular dynamics. M is also established from the molecular mass, but Z is more difficult to obtain, this damping matrix. And what one can do there is consider the protein in the fluid, in water, or some other fluid, and then make a finite element model of that situation and obtain basically the Z by imposing unit displacements on the protein. I don't know whether you can see this too well, but here is the protein. All of this is here the fluid. We are taking a fine mesh around here, then a coarser mesh, and then a very coarse mesh. This is all fluid. Far away, the boundary, of course, is far away from the actual protein. You use mesh gluing here in order to obtain, go from the fine to the coarse mesh. We are imposing unit velocities on the fluid, on the protein surface, but for Stokes fluid, which we assume here, that can be done very efficiently by actually using a structural analysis code. We're using ADINA to obtain the Z matrix here, because we can assume a Stokes fluid. And then we have a symmetric a K matrix to simply get the Z very efficiently. This is then the analysis that we obtained from Brownian dynamics of a protein. And of course, having got this movie, we don't really know how accurate the motion of the protein has been represented. So we need to somehow seek another way of evaluating the quality of the results. And what we do is we actually go through to analyze the diffusion properties. Let Z curl Ij, given here, simply be the force at node I due to unit velocities at node J. And then we define this matrix here, which gives coordinates, and obtain this resistance tensor here, where you can see these are simply forces, these are moments, and these are second moments. And this resistance tensor then can be used to obtain a diffusion tensor by this relationship, a generalized Einstein relationship. And this diffusion tensor here, these properties here, or the numbers that we are obtaining there, they can actually be measured in the experiments. And now we are able to compare with actual data. And you can see here the comparison for, as a function of molecular weight, of the diffusion constant for different experimental results on different proteins. 10 proteins we're actually looking at here, and the thicknesses with which the surface has been modeled there. So you can see that we're comparing quite well on these constants, and that then also gives us some satisfaction that our results of the Brownian dynamics are actually quite acceptable. However, I like to also point out that proteins have for decades been analyzed and studied in vacuum, which was very, very valuable. To go and put a protein into a fluid and analyze it is much more complicated. So we wanted to, of course, now see how do our results of the protein in the fluid compare with the protein simply analyzed in a vacuum. And for that, we simply calculated the eigenvectors, assuming a vacuum, and then the eigenvectors assuming that the protein is in a fluid and, of course, under Brownian motions. And then we can establish a modal criterion, and this modal criterion tells us really how are the vectors, the eigenmodes, comparing. We find that there is very little comparison. For a perfect comparison, we would have these red dots right along here, because we have the vacuum normal mode number here and the Brownian normal mode number here, and we would have, for perfect comparison, or for the mode shapes to be similar, we would have to have on the diagonal all these reds lying on the diagonal. And we don't see that at all. So basically, what we are saying is that if you want to have a reliable understanding of proteins in motions, you really have to go towards modeling them in the fluid. Although, of course, a lot of insight can be gained also by just looking at the motions in the vacuum. DNA structures. The dynamics of DNA structures we are analyzing the same way as for the proteins, using Brownian dynamics. And here are some simple DNA structures that could, for example, be used for small medical devices that are implanted in veins and so on. Here's a tweezer which we analyzed with molecular dynamics and Brownian dynamics. The Brownian dynamics that I just mentioned, and also molecular dynamics. The relaxation time is about 42 nanoseconds. It's the largest relaxation time. We wanted to calculate 6 microseconds, and so we needed about, with a time step of 4 picoseconds, we need about 1.5 million steps. When we do such a run, it takes 32 hours on a single processor machine. With our Brownian dynamics solution, BD of course is Brownian dynamics up there. When we analyze that same situation in molecular dynamics with an explicit atomic model, putting in other words all the effects into the molecular dynamics, then the run took 36 days on 100 CPU cores plus 10 GPU units. So a lot of computing power was applied to simply perform for this rather simple structure the molecular dynamics solution. And that tells that you cannot really go to more complex structures with the molecular dynamics analysis, because 100 CPU cores plus 10 GPU units, it's a lot of compute power. Oops. We then compared the molecular dynamics and Brownian dynamics solutions, and we can, again, the relaxation times, as I pointed out, are the ones that we can easily compare. And we compared the Brownian normal modes, the molecular dynamics essential modes. Basically, you look at the molecular dynamics response and you extract from it the modes that you can identify in that response. And then also, of course, we do the same for the Brownian dynamics response. You extract the modes from it, and you can also obtain the relaxation time simply from the eigenvalues, from the eigenvalue problem. And clearly the red and from eigenvalue analyses, they must lie pretty much on top of each other, as they do. The molecular dynamics essential modes are giving us relaxation times quite close here for the lowest mode numbers, but the higher mode numbers there is, of course, an error. But still it is, since we are primarily interested in the lowest mode response, it shows that this approach that we're using is quite efficient there, but of course it can also still be improved. We then went to a slightly more complex structure. We did a Brownian dynamics simulation of this layered ring. The solution time was a few days with our Brownian dynamics solution approach. A molecular dynamics solution we could not perform. We estimated that it would take over 10 years, maybe almost 100 years. And we can't wait that long. So it's interesting to see that the compute power being so big, there are still a lot of problems that can simply not be handled. I'd like to conclude now that very powerful capabilities are now available, that there are still many exciting research challenges, a message to our young in age and heart researchers. I think there's a lot more exciting research in the field. I personally believe that we're really only at the beginning of the use of simulations on the computer and the extent to which these will greatly enrich our life. And that's all what it's about, to enrich our life. Thank you for your attention. I'd like to also mention once here again, many students and other collaborators have contributed. As I pointed out earlier, please look at the page, my page on the MIT website. Thank you very much. Merci beaucoup.
Allô, vous m'entendez? Thank you very much, Jürgen, for this quite broad application of computational mechanics, starting from a simple truss element to a very exciting new application in molecular dynamics, Brownian dynamics, and application in for the simulation of the behavior of proteins and other things. It's I can understand that this is a very exciting field for you, and I am sure you will be most pleased to work with your son on such a subject. Okay, it's open for discussion. We have plenty of time, so don't hesitate to ask questions on any subject related to computational mechanics. Since there is no limitation in what you have done regarding the physics, chemical aspects, multi-physics, so I am sure there will be some comments and questions. Il y a des micros qui peuvent se promener. Une petite présentation de chacun des intervenants.
Professeur François Trochu, École Polytechnique de Montréal. I really enjoyed your talk and also the conclusion, pointing out that the limitations of the solving finite element problems for very large structures. Actually, we encountered that in a practical problem, just simulating the heating of a real mold for composite manufacturing. And I was surprised to see that we were very limited in terms of response time by, let's say, commercial codes. So my question is, what would be, in your opinion, the trends that would help in the future to improve these codes so that we can really tackle very large problems?
Yeah, that's a very, very nice question. Thank you. I think we need to really work on different fronts. The very large problems, of course, need new numerical methods, but they also need more compute power. I think that our numerical methods at the moment do not yet take full account of all the compute hardware, for example, that's available. The parallelization is one problem. We want implicit time integration. We want static analysis, of course, being parallelized. We have these big matrices, the K matrix. And to parallelize that in SMP, shared memory processing, it has been done, works quite well, up to a certain number of processors. When we want to go to distributed memory processing for implicit schemes, very difficult to obtain really the speed up that we like to see. So there's a lot more work to be done, I feel, in that area to simply make our algorithms more parallelizable for DMP. I'm thinking, for example, on large eigenvalue problems, something also close to my heart. There are methods, like the Lanczos method is used now quite widely. It cannot be very nicely parallelized in DMP because you're always looking at one vector at a time. I believe that there is room to improve our methods, our numerical schemes, substantially still, to be much more parallelizable. So it is really a matter of pushing the numerical schemes forward at the same time, of course, as the compute hardware will be pushed forward as well. We are not taking yet full advantage with our numerical schemes of the hardware that's actually available already. That's one answer. And then, of course, we need better numerical methods. Methods that also require less dense grids. For example, I mentioned the method of overlapping finite elements. And if you're in practice, maybe you appreciate particularly what I mean. What's being done now typically is that people spend a lot of time on meshing. You have a CAD geometry, you mesh that CAD geometry, and somebody might, for complex geometry, spend many weeks to mesh. I believe that we need to think totally different in terms of meshing to bring down the solution time, the total time of actually analyzing. I foresee that what we would like to have is, for a complex 3D structure, that we simply have Cartesian grids running in all directions, a Cartesian grid, which the engineer will just have a slider, how many grid cells she or he wants into this direction, another slider, how many in that direction, and how many in that direction. That sort of Cartesian grid, simply putting the whole structure into that Cartesian grid to generate takes seconds today. What do? Then you need to have, of course, the boundary representation. So you have the Cartesian grid overlaid on the structure, and the boundary, I think, has to be picked up by what I think being these overlapping finite elements. In other words, the boundary is discretized. The engineer will say, I want in 2D so many such spacing on the boundary, in 3D a certain size of facet representation on the boundary, and then the boundary is simply meshed inside, a little bit towards the inside, but only on the boundary, and then, of course, the boundary elements will overlap the Cartesian grid. The Cartesian grid will work very well because it's non-distorted elements. I showed some results with the shell elements. The shell elements work much better when they are non-distorted. 3D elements work much better when they're non-distorted. Fluid flow. In fluid flow, you want to have non-distorted meshes. You can take much coarser meshes. And so I really believe that this approach that we're working on, where we take a Cartesian grid in all directions, very quick to generate, and on the boundary, these overlapping finite elements, all operating, that's in addition, on the CAD geometry directly. You're operating on the CAD geometry. So basically, the mesh is being constructed directly operating on the CAD geometry. The CAD geometry might be somewhat dirty. It doesn't matter really, because the engineer can say, I want that sort of discretization on the surface. And if there's some dirty, not closing CAD geometry, the discretization will just walk over it. So this is where I think lies the future of analysis. Then 3 months of meshing plus 1 day of computing might mean 1 day of meshing and 1 day of computing, or 2 days of computing for big structures, and that's fine. But you have basically compressed 3 months down to 3 days.
D'autres questions? Michel.
Well, you gave a very nice lecture, but I'm not really myself in a position to ask questions. But I believe that we have common friends because I spent more than 8 years at MIT from 62 to end of 64, where I did my PhD with Ronnie Probstein, whom I'm sure you knew.
Of course.
And also I have other colleagues like Forbes Dewey. They were also Ayn Sonin and Asher Shapiro. You knew them, yes. So what I wanted to know if they are still going well, I suppose. You have...
I'm sorry, I can't give you too good news there.
Yes, I know that. I know that.
Asher passed away.
Yes, but.
Ayn also passed away.
Who?
Ayn Sonin.
Yes, I know. I know that Asher and Ayn Sonin passed away, but Ronnie Probstein is still okay, more or less. Yes. No, we have, very good friends, and my wife and his wife exchange emails every week. Also, I was interested that you worked at Cape Town University.
Yes.
Because I had a collaboration during 5 or 6 years with Professor Peter Swart. I suppose you know him also.
Yeah.
Yes. Okay. Well, thank you for this. So you should send them my greetings. You see, Peter Swart and Forbes Dewey also. But thank you for your lecture.
Forbes Dewey is doing well. He's retired, and he has his office now right next to my office. Okay. Forbes Dewey. You mentioned Forbes Dewey. Yes. Yeah. So he's. I just saw him last week. Yeah, so he's doing well.
Merci, Michel. Oui? Okay.
Thank you. I'm Pierre Villon from UTC. You know that we worked on meshless method. Finance fair method is one of the meshless method. We have big troubles with numerical integration, special numerical integration. And you speak about some new accurate procedure. Can you give some details on that, please?
Yeah, I think you might notice that I am more interested in using the meshless type of approach around the boundary, which cuts down the number of meshless elements, so to say, you use. And it's precisely because the numerical integration is very expensive. It's expensive in 3D analysis of statics. However, in wave propagation problems, it's not that expensive because you're setting up the K matrix once. And then you'll run 1,000 steps, 5,000 steps. And you have a smaller K matrix, smaller than in the finite element analysis, and that's where you gain then a lot of time. So there are certain types of applications where I think the meshless method, as it stands now, some meshless methods, I think are very attractive. Not all. What type of integration do we use now? A very simple one. We basically use Gauss integration of a high enough order for all the different sectors that have to be integrated.
The sector of the length of the sphere, the critic spheres, intersecting spheres?
Yeah, we do Gauss integration. We do Gauss integration, but of course we are only integrating over those points that are actually in the domain to be integrated. And it's not very efficient. There's a lot more ideas hopefully coming out. I'd like to talk with you about that detail. That has to be improved still. But even though I really believe that if we use this approach that I mentioned, only on the boundary, this meshless type of overlapping, it will be only 5%, maybe less, of the total domain that is meshless. I think it will be efficient. The solution time might go up, obviously, but remember, the total meshing time is drastically reduced with the approach that I mentioned, drastically reduced. And I think that makes it very, very, very efficient and very attractive to engineers.
But the devil is in details often.
Oh yes, of course. Absolutely, it's always in the details. The devil is always in the details. Absolutely.
Maybe the last one.
So I am a professor on noise and vibration. So I would like to ask you a question on how, for example, solving a problem by boundary element and combination between boundary element and finite element methods. Have you experienced that?
I have myself not worked on boundary element methods. I have followed what has been done. A lot of very interesting research has been accomplished. There have been programs developed also, the BZ program and so on, using boundary element approaches. I was more interested in a very general approach, which can be used for linear, non-linear analysis, contact problems, fluid flow, and so on. And boundary element methods, to me, are probably most efficient for certain types of problems. Linear statics of 3D, very efficient, can be very efficient for certain types of problems. But I have not worked myself in that area.
Thank you. I think we should close the discussions so that we have some free time before lunch. So thank you again, Jürgen. And Jürgen will stay, of course, this afternoon and tomorrow, so there will be additional occasion to ask questions to him.
Thank you.